Okay then, good evening Carolians. I realise the time, and so I'm going to try to get through this even faster than usual. So I'm talking about the beginning of everything, the beginning of the universe. It took 3 minutes to make the universe. I'm going to give you a recap in perhaps a little bit more than 3 minutes. So what am I talking about? The creation of the universe. When did this happen? 13.8 billion years ago. How long did it take to make a universe? About 3 minutes. Where did the Big Bang happen? Well, the Big Bang happened everywhere because it was the creation of everything. And why did the universe evolve the way it did? Because of the laws of physics. And how do we know all this? Same answer, because of the laws of physics. So if we think of the universe as a chess game, we can ask ourselves, well, we can look at the universe, but can we figure out what the rules of the game are? Can we figure out how the universe came to be and how the universe ended up looking like it does? With chess, a single picture doesn't tell us the whole story. Similarly, looking at a single galaxy doesn't tell us what's going on. The galaxy hardly seems to move, and we can't really take a video of a galaxy evolving. But what we can do is take a snapshot of the universe and look at lots of galaxies, some close to us, some further away, and because of the finite speed of light, that means we can effectively look back in time. Maybe I shouldn't be showing a Hubble deep field at this point, maybe I should update it with the Webb deep field. A similar picture, again, looking back many billions of years. We can ask ourselves, surely the universe is too complex to understand. Well, if we think of this particular collection of mathematical points, the so-called Mandelbrot set, here we have an infinite number of pixels, only some of which are shown in this particular picture. It's an infinite set of pixels that are coloured according to a certain formula. And no matter how much we zoom into this particular set of pixels, we see more and more and more detail. It is infinitely complex, infinitely detailed. So how complicated must the formula be that generates each and every pixel in an infinite pixel set, such as this? Well, the formula that generated the Mandelbrot set is that one. Z equals Z squared plus C. We don't have to worry about what the symbols mean. The point is, an extremely complex system might be the result of a very simple formula. So although everything we see in the observable universe appears to be very complex, it might be that we can figure out what the rules of the game are. One of my favourite quotes of Einstein, the most incomprehensible thing about the world is that it is comprehensible. Just because the universe is complex doesn't mean we can't understand it. So here's the flow of thought. Observation. We look out into the universe and we see that galaxies are moving away from each other. We've known that for 100 years or so. We conclude that the universe must be expanding. And experiments we can do here on Earth, such as particle physics experiments in an accelerator like the Large Hadron Collider, tell us about the nature of matter and what the world is made of. And we assume that the rest of the universe is made of the same stuff. We must make another assumption, and that is the laws of physics that we see here on Earth must apply everywhere. Also, the laws of physics that apply now are the same as the laws of physics in the past and in the future. In other words, the laws of physics don't change depending on where you are or depending on when you are. That is an assumption for us to make any progress whatsoever in understanding what the universe is all about. From that, we conclude that the universe was created in a very hot, dense state, which of course we call the Big Bang, 13.8 billion years ago, and it's been expanding and cooling ever since. But the big question is, where did all the matter that we see in the observable universe, where did it all come from? When we look out into the universe, we see trillions of galaxies, which probably contain hundreds of billions of stars and probably a similar number of planets. But where did all that stuff come from? How far back in time can we go before we basically give up on the laws of physics? Can we go back to the first year of the universe's 13.8 billion year history? Yes, we can go back to the first year and still be confident that the laws of physics we understand today must have held back then. Can we go back to the first day? Yes. Can we go back to the first hour? Yes. The first minute? Yes. The first second? Yes. Can we go back to the first millisecond after the Big Bang and say that we really do believe we understand what was happening? Yes. What about the first microsecond? Yes. What about the first nanosecond? Yes. What about the first picosecond? Not really. When we get back to the first picosecond, the first trillionth of a second after the Big Bang, we are not too sure what's going on. We're on fairly shaky ground up to the first picosecond. Everything from 1 picosecond, 1 trillionth of a second onwards for the next 13.8 billion years, that is relatively well understood. Not every detail, but the big picture, we pretty much understand what's going on. So in this particular short talk, I've given you a little bit of an introduction. I'm then going to cover one slide of basic ideas and then cover the first fraction of a second after the Big Bang, the first few seconds, the first few minutes, the next 377,000 years, and that's not an arbitrary number. There's a reason for picking that number. And then I'll fast forward the next 13.8 billion years. So firstly, let's just make sure we've got a few basic ideas. This is probably telling you some of what you already know. We are made of atoms. An atom is a central nucleus, positively charged, and a whole set of negatively charged electrons buzzing around. So an atom comprises a nucleus plus electrons. An electron appears to be a fundamental particle in the sense that it is not made of anything, it just is. You can't take an electron, cut it in half and have a look inside. But a nucleus is different. A nucleus is made of other things. A nucleus is made of protons and neutrons. And these are particles that were discovered quite a while ago, many decades ago. And again, protons and neutrons, unlike electrons, are not considered fundamental. In other words, it is possible to ask what is inside a proton, what is inside a neutron. And they are made of particles that we call quarks. This is not a particle physics lecture, so we're not going to worry about what quarks are. We're simply saying that quarks are fundamental particles which make up protons and they make up neutrons. Protons and neutrons together make up a nucleus plus other particles called electrons make up atoms, and of course atoms make molecules which make us and pretty much everything else we see around us. The amount of energy required to take an atom and separate it into a nucleus and electrons, well, a certain amount of energy is required to do that. But the amount of energy required to take a nucleus and break it down into its constituents is even larger. And the amount of energy required to look inside a proton and see what it is made of is larger still. So there's an implicit energy scale from low energy, large structures, to high energy if we want to get inside smaller and smaller and smaller structures. And remember, the universe was made in a very hot, dense state, and for a physicist, hot means high energy and cold means low energy. So if there's an energy scale here, and we know the universe was made very hot and is cooling down as it expands, then there's also a time scale here, from the past at the bottom to the present at the top. In other words, the universe was made from the bottom up. In the early days, it was simply too hot to make an atom. If you tried to make an atom in the early universe was so hot, there was so much energy, the atom would have been ripped apart. And in the very early universe, it was simply too hot for quarks to get together to make protons. So as the universe cools, particles like quarks make protons, and then eventually the universe is cold enough for protons and neutrons to get together to make nuclei, and eventually the universe will cool a little bit further and a nucleus will hang on to electrons to make atoms. So it's a sort of Russian doll, and we're working from the inside outwards, in this diagram from the bottom up. So that's the basic idea. If we keep that Russian doll model in our heads, then hopefully what comes next makes a little more sense. We can ask ourselves what happened at the instant of creation, at t = 0. And I'm sure that you realise science does not have a definitive answer to what happened at t = 0. It is widely believed that you can indeed get something from nothing. So it's very difficult to talk about what happened before the Big Bang because time didn't exist in the way that we generally think of it on a day-to-day basis. But quantum mechanics tells us that it is possible to make something from nothing. We believe it's happening all the time. Quantum mechanics, or quantum theory if you prefer, is indeed really weird. And the idea of making a universe from nothing sounds like a complete and utter cheat. But quantum theory tells us this is perfectly okay. It doesn't agree with common sense, but then quantum theory doesn't agree with common sense, which means common sense is wrong. Because quantum theory, as far as we know, is right. So we can't be definitive, but we believe that that might have been the origin of our universe. Now we're going to fast forward to a time of that many seconds, a ridiculously short time of 10 to the minus 35 seconds, at which point everything that we now think about as being inside the observable universe, the observable universe is currently a sphere of diameter approximately 100 billion light years. And we think that at the time of about 10 to the minus 35 seconds after the Big Bang, everything that we currently see inside the observable universe used to be a lot closer together. It used to be in a volume approximately the size of a golf ball. That takes a little bit of imagination, I agree. But just like a golf ball, the universe at this particular point is not perfectly smooth. The universe has dimples in it. It has variations in density and variations in temperature. Eventually, when the universe has expanded to a much, much, much larger structure, these little dimples in density and temperature will give rise to variations in density that ultimately give rise to galaxies and clusters of galaxies. So let's move forward to 1 picosecond. Up till this point, it's been conjecture, it's been hypothesis. But from 1 picosecond onwards, we think all of this is established as close as fact as we can get. 1 picosecond after creation, the universe has expanded to be about the size of the solar system. Yes, the solar system doesn't yet exist, but you get an idea that the expansion has been very rapid. In a tiny fraction of a second, the universe has expanded so that its size is now many, many light hours in size. So clearly it's expanded much faster than the speed of light. The temperature is continuing to fall as the universe expands. The temperature is now about 10 to the 15 Kelvin, and the energy of each of the constituents in this soup of particles that were generated by effectively borrowing energy from nothing and using that energy to make particles, this is a soup of particles which I'm going to call the quark soup. It's effectively a soup of any particle that can be made from the energy that you've borrowed from nothing. This something from nothing idea. Doesn't really matter what the particles are. What matters is the fact that the energy of each of these particles at this temperature of 10 to the 15 Kelvin, the energy of each of these particles is about the same as the energy of the particles that can be sent around the Large Hadron Collider. In other words, from this point on, we're dealing with energies which we can actually achieve on Earth. We can test ideas by smashing particles into each other at these energies and see what happens. So that is why I say that after a picosecond, we've got a reasonable idea of what happened, because everything from this point onwards is testable. Everything prior to a picosecond is hypothesis, and we don't actually know if it's right or wrong. So because we can test our ideas, we've got a reasonably good idea from this point onwards of what happens. We've borrowed energy from nothing, and that energy is being used to make matter and antimatter. Antimatter is just the opposite of matter. For every particle, such as an electron for instance, there's an antiparticle. It looks just like an electron, but it has the opposite charge. So that's what we call antimatter. Matter and antimatter originally are made in equal amounts. So a certain amount of energy, I don't know how to represent that, so I'm just going to use the capital E to mean a certain amount of energy. Energy can be used to make matter and antimatter. probably not an orange and an anti-orange. It's probably going to be a quark and an anti-quark, or an electron and an anti-electron, or some other particle and its anti-partner. It doesn't actually matter what the particles are. They are made as a matter-antimatter or a particle-antiparticle pair, and then very soon thereafter they annihilate and produce energy. In other words, there's a cycle. Energy creates matter and antimatter, they annihilate and produce energy, which again is used to make particle and antiparticle pairs. Probably not a hot dog and an anti-hot dog, but it doesn't actually matter. This process is going on and on and on, matter converted into energy, energy converted into matter. This is going back and forth, essentially continuously during this early phase of the universe. Somehow, and we don't really understand the details of this, somehow matter gains an excess over antimatter, and we'll return to that issue a little bit later. So in other words, although we think we're making a lot of matter and a lot of antimatter, we're not making quite the same amount of both. I've indicated here that matter is a 10% excess over antimatter. It's not quite that big. It's not 1 part in 10, the extra bit of matter. It's more like 1 part in a billion. So the imbalance exists, but it's actually quite tiny. But you can see what's going to happen if you let time go forward a little bit. Matter and antimatter particles are going to annihilate and produce energy. But there's going to be a little bit of matter left over, because more matter was made than antimatter, so there's a little bit of matter that doesn't have an antimatter equivalent to annihilate with. That means you end up with a universe which is full of energy in the form of light, and a little bit of matter is left over. That is you and me and the Earth and the Sun and the Milky Way and the other trillion galaxies that we see in the observable universe. Everything we see, all matter that we see, is that little bit that was left over, that 1 part in a billion imbalance in this very early stage of the universe. If we fast forward now to a millisecond after the Big Bang, matter and antimatter are continuing to pop into and out of existence. And because the temperature has now fallen a little bit, it's possible for quarks to get together into groups or into configurations that we give particular names. We're not going to worry about the details of the quarks, but when certain quarks get together, we call that collection of quarks a proton. So on the left-hand side, a particular collection of quarks, if you like, in a bag, we call a proton. And a different arrangement, a different configuration, if you like, of quarks is what we call a neutron. We're not going to worry about why those 3 objects have labels of D and U, and we're not going to worry about why some of them are coloured red, some are green and some are blue. All that matters is a certain collection of quarks is called a proton, a different collection of quarks is called a neutron. And because we have this soup of matter and antimatter popping into and out of existence, effectively protons are changing into neutrons back and forth, as indicated by the blue arrows in the middle there. In other words, protons and neutrons are a fluid idea. They are continually changing into each other and back again. If we move forward to about 1 second after the Big Bang, the universe has expanded and now cooled to about 1 billion Kelvin. That might sound rather a lot, but bear in mind that could be the sort of temperature at the centres of some stars, so it's not completely out of reach of modern ideas. Now that the universe has cooled to 1 billion Kelvin, it's actually too cold for protons and neutrons to readily swap backwards and forwards. Remember, the more energy they have, the easier it is for them to change from one to the other. But if the universe is now cooling off, it's rather difficult for protons to change into neutrons and vice versa. So at this particular point, the universe hasn't made equal numbers of protons and neutrons. Why is that? Because protons are a little bit lighter than neutrons. They are about 0.1% lighter. How do we know that? Because we can measure it in the laboratory. And as far as we can tell, a proton and neutron that we measure today are exactly the same as protons and neutrons that existed 1 second after the Big Bang. So if protons are a little bit lighter than neutrons, then the universe is going to make more of them. Protons outnumber neutrons in the ratio of 75 to 25 out of every 100. Or if you prefer, 12 out of every 16 particles are going to be protons and 4 are going to be neutrons. From here on, I'm representing protons as these red objects and neutrons as these blue circles. Why does the universe prefer to make lighter particles? Well, just because it's easier. Nature always favours the lower energy. In other words, in this case, lower energy is the same as lower mass. So just like if we take an object and drop it, it falls because a lower position for an object in a gravitational field is a lower energy than a higher position, which is why objects are attracted towards the Earth. So nature always takes the easy way out. It always favours the lowest energy, and in this case that means favouring the lowest mass. So because protons are a little bit lighter, the universe makes more of them, and the prediction is there ought to be 3/4 of the universe protons and 1/4 neutrons at this stage, 1 second after the Big Bang. If we move forward to a couple of minutes or so after the Big Bang, we find that some neutrons have changed. We know that neutrons are unstable. Again, we can measure that in the laboratory. Some neutrons will change into protons. So originally there were 12 protons and 4 neutrons, but now the ratio has changed. Two of those blues have changed into reds. So now we have 14 protons and 2 neutrons. And that is pretty much the ratio that must exist from this point onwards. The universe has now cooled to 100 million Kelvin, and we are not going to make any more protons and we're not going to make any more neutrons. But now that the universe is a bit cooler, protons and neutrons would really like to get together. 2 protons and 2 neutrons make a very stable structure if they're allowed to, and at the moment we have a whole number of protons and neutrons, so they will get together if they can. But of course there aren't the same numbers. Although 2 protons plus 2 neutrons is very stable, we call it an alpha particle. That's a very stable structure, but of course there aren't enough neutrons to go round. So what happens is that 2 protons end up combining with 2 neutrons to make either what we call an alpha particle, or what we could label as the nucleus of a helium atom. But of course we're then left with 12 bachelors who can't find any neutrons to pair up with. They can't marry a neutron because there aren't any left. So what you end up with is a universe full of a particular ratio of individual protons, otherwise known as the nuclei of hydrogen atoms, and a particular number of nuclei of helium atoms. And we can see there are 12 nuclei of hydrogen for every 1 nucleus of helium. Or in terms of mass, the universe should be 3/4 hydrogen, 1/4 helium. After about 3 months, after about 3 minutes, not 3 months, after 3 minutes, the universe is too cold to change that ratio. The relative abundances of hydrogen and helium are now fixed. The universe is too cold to change that. All of the creation of hydrogen and helium happened in the first 3 minutes. And from 3 minutes up to where we are now, 13.8 billion years later, that ratio can't change, except for the fact that stars will start to change one element into another. But in terms of how much hydrogen and how much helium is out there, when we look at the universe on the largest of scales, the actual amount of hydrogen that's been processed by stars is actually quite small. When we look at the amount of hydrogen and the amount of helium in the universe as a whole, the fraction of hydrogen to helium appears to be 3/4 to 1/4. Just as predicted by this idea of how many protons and how many neutrons are we expected to be made in the early universe, and hence predict how much hydrogen and how much helium. The fact that this theory correctly predicts the abundance of hydrogen and helium is one of the reasons we believe that the Big Bang theory is the best theory to explain our universe. It gets that particular prediction correct. Let's really fast forward now after 3 minutes. Let's fast forward another 377,000 years. Nothing much happens for the next 1/3 of a million years. The universe will continue to expand, the universe will continue to cool. But something important happens when it reaches a temperature of about 3000 Kelvin. Why is that important? Well, at this temperature, nuclei can actually hang on to electrons. Before this point, the universe was so hot, 3000 Kelvin or hotter, that's hot enough to strip any atom of its electrons. In other words, a nucleus can't hang on to electrons if it's hotter than about 3000 Kelvin. But once the universe is this cold, 3000 Kelvin, it's possible for a nucleus to hang on to electrons and hence make atoms. A nucleus of helium can hang on to 2 electrons, a nucleus of hydrogen can hang on to 1 electron and make atoms. So the universe changes from a plasma, a collection of positive and negatively charged particles, it changes into a collection of neutrally charged atoms, because the positive nucleus is now balanced by a negative electron. So for the first time in history, if you like, the universe becomes transparent to light. So up to this point, light has been rattling around like a ball in a pinball machine, bouncing off all of these charged particles. But as soon as the universe becomes transparent, it is possible for the photons of light to go flying off through the universe. And that light that was released at this particular point, 377,000 years after the Big Bang, that light has been stretched by the subsequent expansion of the universe. At this particular point, 3000 Kelvin, the universe would be white hot. There would be a lot of visible light floating around. But that light has been stretched out by the expansion of the universe and is now a wavelength 1,000 times longer. So instead of having a wavelength of about 1 micron, the wavelength of light, visible light, that light has been stretched to a wavelength of order millimeters rather than microns. And that is what we see. This millimeter wavelength light is what we call the cosmic microwave background. The light that was released at the instant or the time at which the universe became transparent. And we see that as microwaves. This is an all-sky map telling us that the amount of light coming from different parts of the sky, it's approximately the same amount all over the sky, but this map is exaggerating the tiny differences that some parts of the sky are a little bit hotter, a little bit more microwave radiation, other parts of the sky are a little bit colder. And that's the result of the dimples in the original golf ball. Remember, the golf ball had dimples, variations in intensity and temperature. That is what we're looking at when we look at the cosmic microwave background. Those dimples have been, in a sense, imprinted into the microwaves that were released, the light that was released at the point at which the universe became transparent. And again, that's why we think that the golf ball, the hypothesis of this golf ball that existed in the very early universe, must have had dimples, because when we look at the cosmic microwave background, we see those dimples. So that's why the cosmic microwave background is being studied. Small variations are the result of these dimples, and hence if we use a satellite, the cosmic microwaves don't make it to the ground of Earth, but if we put a satellite in orbit and look at these microwaves, then by studying the microwave background, we are looking at the very, very early universe, only hundreds of thousands of years after the Big Bang, which is why people are very interested in studying in great detail what this microwave background looks like. The dimples in the golf ball that we talked about and the variations that we see in the microwave background over billions of years ultimately make the universe that we see today. If we run a simulation, the link is in the bottom of the screen there, and I'll give you a handout later. If we take a small volume of the universe, fill it with matter, but put in these small variations in density and temperature, i.e. the dimples in the golf ball, and we let gravity do its thing, we find that the small variations in density collapse into a structure of filaments, and voids, and where these filaments seem to intersect, we get rather high density of material forming. Material is effectively flowing down the filaments and collecting in these areas, which are ultimately these white blobs. These are the regions where galaxies and clusters of galaxies and individual stars ultimately are being made. And this structure is, roughly speaking, what we see. When we look out into the universe, the galaxies aren't smoothly distributed throughout the universe. They seem to be clustered into these filaments and voids that we can calculate using computer simulations, using large supercomputer simulations. Now that we have hydrogen, we make the hydrogen in the first 3 minutes, and we understand that process based on our understanding of the cosmic microwave background and the simulations that tell us what's happened since then. As long as we start with shed loads of hydrogen, then we can pretty much understand everything. As long as you've got lots of hydrogen, then we understand basically the formation of galaxies, or at least simulations will help us understand the formations of galaxies. And if you put a lot of hydrogen in one place, you can make a star, which is fusing hydrogen and making more helium. And basically, given hydrogen, we can understand galaxies and stars and planets and trees and mountains and snowflakes and rainbows and cats and okay, maybe not cats. I don't think we'll ever understand cats. But if we start with enough hydrogen, then we can pretty much understand everything that comes after that. Yes, there are still a lot of details to be worked out, but you get the basic idea. But of course, the jigsaw is not complete. There are some rather fundamental questions that still remain. Why did matter win over antimatter? In other words, what caused the asymmetry in the first place? We know that asymmetry must have been there because we live in a universe which appears to be full of matter, and there's very little antimatter knocking around anymore. There is a little bit out there, but there's not that much. We can do experiments in the Large Hadron Collider and we can measure the asymmetry, but we can't understand the origin. Where did it come from in the first place? And I've been talking, of course, about what is out there in the observable universe. But there are some things that we cannot observe directly. What is this dark matter that we've known about for the best part of a century? It's causing clusters to stay together where they shouldn't. It's causing galaxies to rotate at what appears to be the wrong speed. And it appears to be bending light, as we've seen in lensing images, such as the one recently released by the James Webb Space Telescope, for instance. How does dark matter fit into our understanding of the universe? And even more enigmatic, what is this dark energy all about that seems to be causing the expansion of the universe to accelerate? We would expect gravity to be slowing down the expansion of the universe, but the expansion of the universe appears to be accelerating, which doesn't make sense when you think about what gravity ought to be doing. So this talk is entitled The Beginning of Everything, and I've tried to make it clear that we were thinking about the origin of everything that we can see in the observable universe. All the galaxies with all of their billions of stars and planets, and all the gas and all the dust and everything that we can observe. But of course, everything that we can observe is only some 4% of everything that's out there. The other 96%, the dark matter and the dark energy, that of course is still a bit of a mystery. But that's another story. Thank you for listening.